webinar on deploying high-density wireless networks for public venues. My name is Elsa Levy, and I'm part of the marketing team here at iBwave. I'm very happy to say that we have a great participation rate today and a wide diversity of attendees, with many of you joining us from Latin America, Argentina, Brazil, Chile, Peru, Canada, of course, and the US, but also Europe, where it's probably already quite late. So thank you very much for taking the time to join our discussion today. So before we begin, I would just like to go over a few housekeeping items. So first of all, I will be sending a copy of the presentation as well as the link to the video recording of today's session via email tomorrow. So you can watch out for that in your inbox. Also, you're welcome to use the GoToWebinar question panel to ask questions at any time during the session. We'll try and answer as many as we can during the last 15 or 20 minutes of the session or as time allows. Finally, for those of you who might be experiencing some audio difficulties, please note that we will try and speak as loudly and clearly as possible, but please make sure to check your own audio settings on your computer or your phone as you dial in as well. So for today's webinar, I have the pleasure to introduce Vladan Jeromovic. Vladan has 20 years of professional experience in the wireless telecommunication industry, having worked in research and development and strategy and technology consulting. He has 13 years of direct in-building experience and has been with iBwave since 2009. As research director at iBwave, he is the principal architect of RF propagation and optimization algorithm applied to in-building RF design and planning tools. Vladan also develops technical courses offered through the iBwave certification programs and builds custom in-building solutions as part of our professional service portfolio. Vladan holds a PhD from the University of Colorado at Boulder. So Vladan, over to you.
Thank you very much, Elsa. Hello, everybody. Good afternoon. Welcome to our webinar on dense networks, dense wireless networks. And we are going to go through the agenda first. We are going to be talking about our company for a few minutes, iBwave, just in case if this is the first time that you are attending one of our webinars, or if you are not familiar with what we do. And then after that, we are going to go through the agenda for high-density public venues. We will talk about what are design considerations for in-building wireless networks deployed at such venues. We will talk about wireless technologies and spectrum bands that are usually included in those networks. We'll be talking about the solutions that are implemented in the venues of in-building systems. A really hot topic these days is passive intermodulation. So we will touch upon passive modulation and mostly and how it affects link budget. And finally, we will be talking about sectorization, which is very important because it is a topic that also touches on a subject of capacity calculation. First things first, who are we? We are in-building wireless solution specialists. We provide global solutions for in-building network design and wireless lifecycle management. We are a de facto in-building RF design and planning standard in North America and in most of Europe, although we do have a presence throughout the world, which is attested by us having customers in more than 80 countries and nearly 600 customers. We have been given a small cell industry award earlier this year for small cell tool design and technology innovation. You probably have heard of us as through our flagship product, iBwave Design, although we do have a few other products that we also have, like iBwave Unity, iBwave Mobile Planner, and we also offer certification courses. Now let's talk about high-density public venues first. What are they? I have given here examples of public venues that we encounter in our daily life. Those are airports, subways, hotels, stadiums, shopping malls, university campuses, basically large venues that are open to general public. And those are the venues where you can find a large concentration of wireless subscribers. So when we say high density, what we mean is there's lots of people concentrated in a fairly small area, and they tend to stay at that area for a while, generating quite a bit of traffic and causing a burden on macro networks. And in order to lessen that burden, capacity burden, in building wireless systems are built that provide not only a good coverage inside those buildings, but good signal quality, and also relieves capacity glut that exists in macro networks near those large venues. As you can see from those pictures, the public venues are very different. We have a public venue such as subway, which is underground, isolated from a macro signal by the fact that it is underground and by the fact that we have concrete walls that are surrounding it. So virtually there is no signal when you are so deep underground. On the other hand, there is a stadium which is very open air. Most of the stadiums are open air, which is exposed to macro signal quite a bit. And then there is a mixture of both university campuses. They usually are older buildings with thick walls. Their penetration loss is quite high, and yet you have to provide a signal not only inside those buildings but also in between them. So there is an open area and then there is enclosed area with a high penetration loss. You have structures such as shopping malls that may have only a couple floors, and then there's a hotel which may have 20 or 30 floors. So they're quite varied, and the question is what is common to them? And we are going to cover that in the next several slides. The design considerations. First of all, what we need to look into when we are deciding to put an in-building system in a public venue is the wireless technologies that should be put in that system. And they should mimic wireless technologies that are already existing in that particular metropolitan area, as well as spectrum bands. What we want to achieve in a public venue is continuation of the wireless coverage that already exists in the macro world. And to do that, we have to include all wireless service providers that provide service in that metro area. That is ideal. And because you do not want to have your general public that is subscribed to one wireless service provider to have good coverage inside the building, and then the other one that is subscribed to a different wireless service provider to have a poor experience inside the venue. Because you want your customers, all your customers, to have a good customer experience while inside the venue. We're going to look into the types of in-building solutions for public venues, what is at our disposal to provide such service. And then we will going to look into passive intermodulation. This is important because we need to provide a variety of wireless technologies in a variety of spectrum bands, and such system is called a neutral host system, which shares network facilities with amongst the network tenants. Now, this is a fertile ground for causing the passive intermodulation, which brings interfering signal from one wireless service provider to another. So we need to look into what causes passive intermodulation and how we can mitigate that, and how dealing with passive modulation is going to affect your coverage. We are going to give example of a link budget and we will see how what we have learned in passive modulation is going to be implemented in calculating link budget. And then finally, we will touch upon sectorization and what are determining factors in figuring out how many subscribers you can assign to a sector. And we will give some examples of sectorization in a large public venue. Now let's take a look at wireless technologies. We have shown examples here as to what we have in North America, Europe, and Asia. And what is common with them is that trunked radio systems that are being used by first responders exist in all those three continents, and they pretty much have to be included in every public venue for first responders to be able to communicate freely once they are inside the venue. Then what needs to be included is 2G, 3G, and 4G technologies. So what we have there is a GSM, and this is 2G, UMTS and HSPA, which is 3G, and LTE, which is 4G. On top of that, in North America, we have a flavor of 3G, which is CDMA 2000 and EVDO. And in Asia, we have AX, GP, and PHS, which are local technologies for 3G. And finally, there is another standard, which is not mobile wireless standard, but it is really omnipresent these days. It's 802.11, or commonly known as Wi-Fi, and is present in many venues. So when designing for 802.11, designing for a public venue, 802.11 should be included. It doesn't have to be included throughout the venue. It can be included in hotspots depending on what kind of demand there is from the building manager, but it should be present in some form because people are now used to having Wi-Fi when they are outside of their homes, inside venues, in cafes, in restaurants, and even in bars. So why not at public venues as well? As for the spectrum bands, we see that there is a large variety of spectrum bands that needs to be covered as well. VHF and UHF are the ones that are given to first responders, and so is SMR 800 megahertz. What we can see is that the variety of spectrum band that exists throughout the world. We have, for example, 4G, which is at 700 megahertz in the US, and it is at 2.6 gigahertz in Europe. Not only that, in US it is FDD, and in Europe it's TDD. So the variety of spectrum throughout the world just attests to that it is a patchwork of spectrum, but it also needs to be taken into account when in deciding what to include in building network. Just because 2G spectrum does not have that many subscribers anymore does not mean that we should easily discard that technology or a spectrum where it is mostly applied. And on top of it, we see that we have a couple of spectrum bands for Wi-Fi that are at a higher end of the spectrum, especially 5.7 gigahertz unlicensed band. So those are the spectrum bands that are for consideration for all those public venues. As we can see, there are plenty of them, and there are plenty of technologies that need to be included. Now, as far as for solutions, the best solution that we see for public venues at this point in time are distributed antenna systems, or DAS, because they can provide a neutral host environment over their cables, coaxial cables, or fiber cables, or KTV. We can send a signal from multiple wireless service providers, and we can have multiple wireless service providers sharing a power amplifier, and that actually helps with the cost, and also sharing antennas helps with the cost and helps with the visual aspect of in-building system, because there are some building managers that are very particular as to how many antennas they want to see at their venue. So there are three systems that we are going to talk about today. One is passive, and even though the name says passive, meaning no active elements, there is a single active element, which is RF source, which is either base station sector or node B or E node B, which feeds a purely passive circuit that consists of of combiners and splitters and dividers and coaxial cables. So what you see here is that the signal will get attenuated both in uplink and downlink in between base station and antenna. What that means that there is a limited distance that these passive systems can cover, and but there is also some good stuff about passive systems, and that is to say that because they have fewer power amplifiers, mainly there is only a power amplifier at the base station, then there is a failure of the amplifier is less likely. On the other hand, when that happens, the whole DAS is down. For active system, what we have is conversion from RF signal to analog to optical digital, and then is sent via fiber, and then there is a conversion on the other end to RF, and then the signal is amplified by the power amplifier and sent via jumpers to antenna. This conversion to digital can take a next step from fiber to actually a digital signal at the low frequency, and then that goes to power amplifier where it gets converted back to RF. So there are two different flavors for active, but the common ground is that there is an active circuitry between RF source and antenna, and there is no passive circuitry between RF source and antenna. So there are no passive losses past RF source. In the hybrid, what we have is very similar, but past power amplifier we have splitters, dividers, and coaxial cables that bring additional loss to the system. What it gives us is more flexibility, because we can apply more splitters, we can apply more antennas to power amplifiers. So that is advantage of the hybrid over active. Now let's take a look at the passive intermodulation, or PIM. So what is PIM? PIM is a product of mixing two signals at different frequencies, and when those two signals are mixed, the product appears in another frequency band. So as an illustration on this picture, which we got courtesy of Enrico, we have two narrowband signals, F1 and F2, and when they are mixed, you can have a third order product or fifth or seventh, as you see. And then even though the amplitude of the mixing product is much lower than the amplitude of either F1 or F2 signal, the bandwidth is a bit wider. And so at the fifth also we have much wider bandwidth, and the seventh much wider bandwidth. So what you see is that the mixing product can actually cover quite a bit of spectrum, and if it happens to fall into uplink band of a different provider, of another provider, then it will generate interference, which will then interfere with the signal coming from UE for that provider, which will then effectively limit the uplink range for that wireless service provider. So how is that PIM generated? Well, there are two ways. There is internal and external. External is generated by objects that are near antenna, and if those objects are oxidized, or as we say rusty, then they have a capacity of generating PIM. An example is a rusty bolt near antenna, or it can be anything else that is rusty. For example, air conditioning box that is rusty will also generate PIM. And then internal sources for PIM are in passive devices, in cables, in splitters, and antennas. Now, how do they generate PIM? Well, if a connector is loose, it is not tightened properly, or if it is tightened too much, it may generate PIM. Junctions of dissimilar metals also may generate PIM, and we already mentioned oxidization. So if there is a rust at connectors, that will generate PIM easily. Another example is ragged cable cuts. This picture that you see, courtesy of Rogers Canada, show what happens, what is a ragged cable cut. Basically, a ragged cable cut is not a clean cut. It shows particles at the location when the PIM was, when the cut was made. And these particles can generate quite easily. So this is how PIM originates. Let's take a look how affects the DAS. It is industry standard to look for a PIM product to be 6 dB lower than thermal noise. And at UMTS we have a thermal noise of neg 107 dBm, and the transmit power is 43 dBm. If we are 6 dB lower than thermal noise, then we are at neg 113, and required PIM suppression would then be 156 dB. And there are passive elements that you can buy that have 155 decibels per carrier suppression when input power is 2 times 43 dBm. Why 2 times? Because remember, we need to have 2 input signals that are going to mix in order to generate PIM. Now for LT, the thermal noise is much lower. It's neg 121, and then we would want, if we are transmitting at 43 dBm, then we have required suppression of 170 decibels below carrier. Now, while we can get on the market 155 decibels per carrier passive elements, we cannot find such elements that have a suppression of 170 decibels below carrier if the input is 2 times 43 dBm. What we can find is 162 decibels below carrier, but at 2 times 35 dBm. And we should deploy those in LT network, but at the same time the transmit power should be reduced to 35 dBm, and that is 8 dB less than what we have at UMTS. Now let's take a look how that looks like in the example when we have a passive DAS, and in this example we have 4 wireless service providers, and their signal is mixed in a 4x4 passive element, and then it is led to 4 different branches when we have 1x4 splitter. So we have 16 antennas, and for this neutral host passive DAS. The transmit power is 35 dBm, and the passive loss, when we take into account those 2 splitters, which is about 13 dB, and then choose 1 antenna and take into account the coax cable loss that exists between that antenna and the base stations, then we get a passive loss of about 18 dB. This gives us the downlink signal at the antenna input of almost 17 dB. And if antenna gain is 3 dB, then our EIRP is on the downlink is almost 20 dBm. If the threshold is neg 85, then propagation loss from antenna to UEE is close to 105 dB. Thermal noise at 10 megahertz channel is neg 104. the transmit composite power is 24, and then uplink signal at the DAS antenna is -1. And signal to noise at the antenna is 23.2. Now when that signal goes through the passive system, then because we apply 18 dB loss, we will get from -1 to -96. And the noise does not change, it stays at the terminal noise, so signal to noise at BTS input is 8 dB. Now let's take a look at what happens if we have a hybrid DAS. What we have is an example when we have remote units connected to those antennas, and those remote units have a transmit power of 30 dBm. With this DAS antenna gain of 3 and cable also 3.5, our downlink ARP is almost 30 dBm. So this is about 9.5 dB more than what we have seen at the passive system. So there is no surprise that propagation loss from antenna to UE is also 9.5 higher. So that is expected for the downlink, that we have a higher propagation loss because we have used the higher power at the remote unit. Now let's take a look what's going on the uplink. What we have is we have remote units that have a certain gain of 15, and there is a noise figure of 7 dB. So this gain and noise figure will raise both noise level and signal level. So when all the calculations are done, we see that the signal to noise ratio that started at 13.5 at the antenna is reduced to 7.8 at the base station. So this is a figure, 7.8 dB, which is comparable to what we have seen for the passive DAS. So as for the uplink is concerned, what we can say is that on the uplink we have about same performance at the cell edge. It's 8 dB for passive DAS, and it is 7.8 dB or almost 8 dB for hybrid DAS. But let's take into account that we have a different propagation loss. In this case, it was about 1.105 dB for passive DAS and 114.5 dB for hybrid DAS. So the antenna range, assuming balanced links, is bigger for hybrid DAS than for passive DAS. Now that difference is about 9.5 dB, 9.6 dB. Now take into account that we could only find passive elements that are rated 162 dBc at 2 times 35 dBm for LTE, and that's why we had to reduce the transmit power from 43 to 35, which is 8 dB. So because of PIM, we had to reduce the transmit power from 43 to 35, and because of that, now in the passive system, our node B is transmitting 8 dB less, and because of that, we see a larger difference in propagation loss between a hybrid DAS and a passive DAS. If it wasn't for PIM, this difference would be 1.5 dB. Because of the PIM, this difference between hybrid DAS and passive DAS is 9.6 dB. So this illustrates how PIM dictates what we can do in coverage, and how it limits the coverage for a particular type of the DAS, which is a passive DAS. Now let's talk about sectorization a bit. This is an interesting topic, and this is something that deals with capacity to a large degree. Now, what factors determine how many subscribers we can fit in a sector? First of all, we need to figure out what are the applications that are going to be used at the venue. And we have a list here: voice, email, web browsing, video chat, data download and upload, video streaming. So first of all, we need to know what are the data rates, the acceptable data rates for each of those. For example, we know that voice is going to have about somewhere in the order of a few tens of kilobits per second, depending on, it depends on what technology you're using, whether it's going to be 12.2 kilobits per second or 8 kilobits per second or 56 kilobits per second. Email and web browsing are at the order of a few hundred kilobits per second, and then it gets higher as you go down the list. Video streaming is very demanding. But what you also need to figure out is which one of those that we have listed is most likely to be used in the venue. For example, in stadiums, you're not very likely to use your phone because of all the noise. You can't hear anything if you try to place a call. But what you would want really to do is to do web browsing if you are attending an NFL game, for example, and you want to know what the updates are. So you will do a lot of web browsing, and then perhaps once you get on some web page that will allow video streaming, maybe you want to even watch some other game while you're attending a particularly boring NFL game. So those are typical scenarios when you see in a venue. If you're in a concert, then you're going to have a lot of data uploads. Voice, not so much. Again, it is loud. Whereas if you are someplace else, like for example in a shopping mall, you are likely to actually call somebody when you sit down to have a drink or to eat something. So those are different for different venues. You need to figure out what is more likely to be used in each venue, and you also need to figure out the duration of usage, or your average call duration for each of those applications during busy hour. As I said, voice calls are not very likely to be made in stadiums, and if they are made, then they are likely to be short. And they're much more likely to be made in shopping malls, and they're likely to be longer. Also, if you are dealing with stadiums, there's usually you have people being in one spot for 3 or 4 hours at a time, whereas in shopping malls, people tend to spend less time at the shopping mall, and they really move around. They're not in one spot, and mostly the data traffic comes from the food court or some other particular area when you have people taking a break from shopping. So that is something that needs to be all determined when you are figuring out which applications are going to be used and for how long. Then what you need to look into is the number of resources available to carry the application traffic. Now, what are the resources? They are orthogonal codes for UMTS, and they are primary resource blocks for LTE. How many of them do you have? It all depends on how many channels, UMTS channels, each service provider has. It also, as far as LTE, it depends on the size of RF channel as to how many resource blocks you have. So those resource blocks and the orthogonal codes, they carry traffic. But the last one, deciding factor is signal to interference and noise ratio. High signal to interference and noise ratio means that higher order modulation is a possibility. And for example, 64 quad. And higher order modulations carry more bits per second per hertz, which means that the primary resource block that is going to be used in a high SANR will carry higher data rate, is capable of carrying higher data rate than the primary resource block, which is in the area where SANR is low. What that means is that, for example, if we are in a favorable spot with a high SNR, I may need only one primary resource block to carry email traffic. If I'm in the area where SANR is poor, then I may need 2 or 3 or even 4 primary resource blocks. And because I have a finite pool of primary resource blocks, then I'm going to be able to serve fewer subscribers if I need to carry multiple primary resource blocks for applications that have a fairly low data rate, such as, let's say, email, for example. So that is, those are three deciding factors that we need to figure out when we are calculating how many subscribers we can put in one sector. In other words, we are doing right now capacity calculation. Now this is a topic that is very interesting, and we are going to cover this topic in more details in our next webinar, when we are going to be talking about designing stadiums. And in that webinar we will show how the call blocking rate is higher for applications that have a higher data rate, which explains very well why is it that you have trouble getting video streaming working while you are at a stadium. And then, speaking of stadiums, here are some sectorization examples of stadiums. There are three types. Sectorization that is horizontal, where we give, which each sector is actually comprises of several rows, several seating rows. And then in this example, there are 4 of them. And you can say that each section is actually covered by one ring, sectorization ring. Then there is a wedge example where sectors are cut like you cut a cake. And this is basically you have people that belong to the same section that are vertically aligned, not horizontally. And both this ring and wedge sectors, it works well if you have a low number of sectors. When I say low number, then let's say if it is several sectors, less than 10. But if you have a larger number of sectors, then you have to do a combination, ring and wedge, which is hybrid. And in this example, I'm showing you how 24 sectors in a stadium look like. Basically, what you have in each level, in each seating level, you have 8 different sectors, and there are 3 seating levels, and those sectors do not repeat. So you do not have the same sector in one area above another. So the total of 24, you may think, well, this is a lot, but we have heard of examples where there is an 80,000 seating stadium that has 60 sectors. If you think about that, that means one sector per about less than 1,500 spectators, which is quite high. And there's a challenge to actually maintain a high SANR when you have such a high sectorization, because of the inter-sector interference that exists in the network. Basically, when you have a sector overlap at the sector edge, you will have a higher interference, which will then degrade the data rate in the network. And with that, I'm going to go over the summaries to what we have talked about. We have given examples of high-density public venues, and we have talked about design considerations for high-density public venues. We talked about wireless technologies and spectrum bands at public venues, what should be included, to illustrate that there is plenty of technologies and plenty of spectrum bands that must be included in in-building network. We talked about 3 different types of distributed antenna systems as solutions for in-building systems, and we have talked about DAS for a couple of reasons. We chose that as a public venue solution because of the capability to carry multiple WSP signals through the network on a common common network elements such as coaxial cables and fiber and cable TV. And then we talked about passive intermodulation, which is inherent to neutral host system because we have so many spectrum bands and we have also large power signals that mix there, and then so which may generate PIM, which actually may produce interference in the uplink if the right combination of spectrum bands presents itself at a neutral host system. Finally, we have given an illustration of a couple of link budgets and shown how the PIM limitation on power affect link budget for passive DAS. And finally, we talked about sectorization, which is a topic that will be covered in even more details, but actually a capacity calculation for sectorization, the topic that will be covered in our next webinar, which will be in the first quarter of 2015. And it will be on stadiums, and if you want to pre-register, you can do so by sending email to marketing@iBwave.com. And with that, I will turn over the microphone back to Elsa for Q&A.
Thank you very much, Vladan, for your in-depth presentation. So we're now ready to take questions from the audience. We've already received quite a few great ones. But if you haven't already done so, now is your chance to submit yours via the question box in your control panel. So I'll start right away. So Vladan, what is the benefit of using DAS over a wideband industrial signal booster?
Of the wideband signal booster, I am not familiar with the wideband single booster solutions. What I'm more familiar is with the solutions where we have separate amplifiers for separate frequency band. For example, for cell, PCS, AWS, or 700. I'm aware that there is an OEM that has a wideband amplifiers, but I myself have not been involved in using that solution in designing a neutral host network.
Thank you, Vladan. John is asking you to clarify, what is the distinction on your slide number 10 between RF jumper and RF coax?
RF jumper is a short 1 meter or half meter cable that has very little attenuation. It's about like a half dB, and it is used to connect antenna with a remote unit. With a particular solution OEM that makes active elements that have a remote units that are meant to be close to antennas. So you basically connect the very low loss cable in between antenna and remote unit. So there is, for that reason, because there is very little loss and because that loss is uniform, it's a half dB, what you have is antennas that are transmitting, all antennas are transmitting about the same EIRP. Now, when you have a coaxial cable between a remote unit and antenna, what happens there is that coaxial cables have a loss of about 3 dB, 3.5 dB per 100 feet. And the distance between a remote unit and a coaxial cable can be 100 feet, 150, can be 50 feet. So you have additional losses. You have additional loss of 2, 3, or 4 dB between remote unit and the antenna. And so there are those additional losses that are significant that you have to take into account when doing the propagation analysis. And then also it will make your EIRP coming from each antenna unequal. So you have to take into account that the longer the distance between the remote unit and antenna, the more attenuation you're going to have in between remote unit and antenna. So that is the distinction. Distinction is coaxial cable will give you significant loss that you have to take into account when doing the analysis, whereas the jumpers, it is just a half a dB. It is not much. You can, even if you forget to take into account half dB, it is not going to have dramatic consequences on your calculations.
Thank you, Vladan. Another question for you. What is the required PIM threshold? What does it need to be lower, 6 dB lower than the thermal noise? Is that a standard value?
We have seen that in the industry. It is not it's not coming from 3GPP, but this is part of the best practices that we have actually seen, and we have actually had a webinar in the past on PIM. If you would want to go back to our webpage and find the broadcast, we had actually a couple of webinars on PIM, if the topic of PIM is of interest to you. And there you will see, how you can, what are the best practices to isolate the PIM, and what are the best practices to avoid the PIM. Now, what happens if you bring PIM level down to neg 127 is your thermal noise is neg 121, and then 127 is 6 dB less. So now when you add neg 127 to neg 121 and you do that in milliwatts and then convert back to dBm, you get neg 120. So your thermal noise level has increased. Your noise raise is about 1 dB, and that is something that is acceptable according to the best practices that we have seen from wireless service providers and system integrators. So that's why we have that 6 dB lower than the thermal noise. This is something that did not come from 3GPP. It comes as something that is as a best practice in the industry.
Thank you, Vlad. And I have another question here from Alfred. Would adding a service provider microcell technology in a building have any impact to an existing DAS?
Okay, so you are adding a new tenant in the building, if I understand correctly, or perhaps you decided that you would want to put a standalone macrocell from a wireless service provider that is not already the tenant. I am not quite sure in which direction this question is coming. So if you can please submit your question, maybe perhaps I can answer via email. But let me just cover something that may be of interest. When these DAS, when they are dimensioned and provided for, they usually make provision for existing wireless service providers in the market. And then so what it means is that they give, for example, more if additional fibers are needed for additional WSPs. They never put like a couple of fiber runs in between, let's say, optical unit and the remote unit. They always have extra dark fiber, okay, in order to accommodate for the future expansion. And then so to a point you can design your system for a future expansion. You cannot predict everything, but it is reasonable to assume that if you have 4 wireless service providers in dominant wireless service providers, or maybe total of 4 wireless service providers in the market, that you would go in and try to design for 4, even though that maybe only 2 have signed on the project at the beginning. You are trying to make it as much of a expansion friendly as possible as a part of your design. And part of it is allowing for things like spare dark fiber, and there are other ways to do that as well.
Thank you, Vladan. Another question for you. Between uplink and downlink signals, which one has a higher power in both wireless technologies?
Between uplink and downlink signal, which one has a higher power? Okay. As for the mobiles, pretty much all technologies limit the transmit power at 24 dBm. Now, as far as I'm assuming we are talking about either hybrid or active DAS. So I'm assuming that you are asking me about the power coming out of the remote unit. Now, that depends on where you want to apply your solution. If you want to apply that in a shopping mall, for example, your antennas are going to be much closer to your subscribers, and you do not want to put a very high power through the remotes because of how close the customers are to antennas. And there, typically what you see as the power coming out of an amplifier in a particular band is of the same order as what you would see out of the mobile. It's about 24 dBm. It does vary with technology a little bit, but this is the typical value between 20 and 24 dBm composite power. Now, if you are trying to cover stadiums, or for example, doesn't have to be a stadium, if you want to cover, let's say, a campus, where you want to cover an area that is outside of those buildings, like usually a quad area, which is in between dormitories, and the areas around dormitories. There, you would want to have a higher power. You want to have, for example, 30 dBm on the downlink because you're covering a greater distances. So maybe even 33 dBm. That is now comes to a point of, what are the distances that you typically want to cover. But this is the general rule of thumb is 30 to 33 dBm if you are deploying it in an area that is transmitting power into an open space. So I have given you an example of a stadium, but another example, that is good. You give an example of campus. The example is stadium as well. And another example would be a subway where you actually want to transmit signal inside the tunnel. And there you would want to have high power transmitting into a tunnel because tunnels are usually long and sometimes winding.
Thank you, Vladan. We're almost out of time, so we'll take two more questions. So what are your views on small cell versus DAS?
Yes, small cells are going to have their place in the future, I believe. And there we already seen the small cells deployment in an outdoor environment. Those picocells that have a coverage of maybe 300 or 400 feet. They already are there. One thing about the small cells is that we have not seen thus far a tendency of having anybody make, let's say, a neutral host small cell. Higher power, when I say higher power, this is what I meant, like 30 to 33 dBm power, maybe a little bit more, of a small cell that will be able to host multiple wireless service providers. So we have not seen that thus far, and we really have not seen any industry movement going into that direction. And then because of that, my view is that the DAS will be around for a bit because it still minimizes the cost of providing multiple signal coverage, multiple wireless service providers over a common network. So the advantage is still there and will be there for quite a bit because we have not seen any signs that small cells are poised to take over that particular segment. Aside from that, it is very promising for different types of venues, not public venues, but other types of venues, like, for example, enterprise venues. We see that it is there is a business case for them there in larger corporations which like to give their employees phones that all belong to the same wireless service provider. It makes sense to go out and deploy small cells that serve that particular wireless service provider for which the company has a contract with at that particular location, which is usually a headquarters or a large office. So there is business for small cells in building, and there is obviously business for outdoor small cells. We just have not seen them moving into this space.
Wonderful, thank you, Vladan. So one final question for you. We have Riyad, who is working on a project where he should give a sharing solution between 3 operators to plan a metro tunnel coverage, 2G and 3G, beside a tetra coverage. So his question is there any risk of PIM or interference which can affect each technology?
Well, to that I will have to say that our solution, I'm proud to say iBwave design, can give you answer to that. We do analysis, PIM analysis in our tool when you design a system and when you connect all your wireless service providers and your tetra sector. It will, and if you choose, when you choose components that you want to deploy, it will give you a warning if your PIM exceeds a certain predetermined level. So if you want to go into particulars as if PIM is possible, my suggestion is, if you are already designing a new building system, is to go and give it a try in our tool and see what the analysis tells you.
Great, thank you very much, Vladan. Our time is unfortunately over, and we haven't been able to answer all of your questions, but we will take the time to respond individually. So for now, I'd like to finish by once again thanking Vladan for his great presentation today, and for thanking all our participants for joining our session. We do hope that you found it informative and useful, and we invite you to join our iBwave LinkedIn group where you can continue the discussion. You can also follow us on LinkedIn, or you can send Vladan an email directly and we'll send you his contact information shortly. Also, just a reminder that we will have another deep dive webinar on Stadium, as Vladan pointed out, in March next year. So you're welcome to pre-register by just emailing marketing@iBwave.com to secure your spots. And finally, you can look for the webinar recording and the slides in your inbox tomorrow. So once again, thank you very much for attending. Have a great rest of the day and a wonderful holiday season. Bye.